Good morning, all. Greetings from Erode Sengunthar Engineering College. I welcome you all to the GATE coaching class. I am M.S.DEVIMANI, working as an assistant professor at the Department of Mathematics, Erode Sengunthar Engineering College. Under AICTE PRERANA scheme, our college is conducting GATE coaching classes. And today's session will be about combinatorics in discrete mathematics for CSE and IT students for writing GATE examinations in February 2021. This is the GATE syllabus in engineering mathematics for CSE and IT students. Here there are four major subjects, that is discrete mathematics, linear algebra, calculus, probability. In this session, we are going to see in discrete mathematics the topic combinatorics. This combinatorics consists of counting, recurrence relations, generating functions. These are the basic counting principles, that is the basics of counting, the pigeonhole principle, permutations, combinations, recurrence relations, generating functions. These are the counting technique we are going to see. The two basic counting principles are, one is the product rule, another one is the sum rule. The product rule states that if one job can be done in m ways and another job can be done in n ways, then the total number of ways in which both the jobs can be done in mn ways. In the same way, we have to state the sum rule as m plus n. The sum rule can be stated as m plus n. That is, here the first job can be done in m ways and second job can be done in n ways. Then there is no way common to both jobs. Then the total number of ways is m plus n. Okay, now we see one example. The example problem is, how many different 8-bit strings are there that begin and end with 1? That is, we calculate how many different 8-bit strings. The given condition is the string starting and ending with 1. Here we know that each bit is either 0 or 1. But the first and 8th place, there is no change. That is constant value. That is 1, and also 8th place is 1. Now we have to calculate the remaining 6 places value. That is second, third up to 7th places value. Each place is either 0 or 1. Therefore, except this first and 8th place, we have to calculate 6 places. Each place is either 0 and 1. Therefore, our answer is 2 power 6. We know that 2 power 6 is 64. Therefore, 64 different 8-bit strings are there that begin and end with 1. Next topic is the pigeonhole principle. The pigeonhole principle states that if n plus 1 pigeon occupies n holes, then at least one hole has more than one pigeon. It is always pigeon is greater than pigeonhole. The generalized pigeonhole principle is, if m pigeon occupies n holes, that is m greater than 1, then at least one hole has more than m minus 1 by n plus 1 pigeon. Here one example is, prove that if 7 colors are used to paint 50 bicycles, at least 8 bicycles will be the same color. We have to prove 8 bicycles will be the same color. Given condition is 7 colors are used to paint 50 bicycles. Here the number of pigeon equal to, we denote number of pigeon equal to m. Therefore, number of pigeon equal to m equal to number of bicycle, that is equal to 50. Number of colors equal to 7. We denote this color by holes, pigeon holes. Therefore, number of holes equal to n equal to number of colors. Number of colors equal to 7. Apply this value in generalized pigeonhole principle. We know that generalized pigeonhole principle is m minus 1 by n plus 1. That is, here m equal to 50 minus 1 by n equal to 7. Therefore, 50 minus 1 by 7 plus 1, that is equal to 8. Therefore, 80 bicycles will have the same color. That is, in pigeonhole principle, always pigeon is greater than pigeon holes. That is at least one greater than Pigeon pole, at least one greater than pigeon holes. The next important topic is permutations. Basically, permutation is an arrangement of objects or any things in a way of order, in a way or order. While dealing with permutation, we should concern about the selection as well as arrangement. Here, ordering is very much important in permutations. Okay, we denote permutation by NPR or P of n comma r. NPR equal to, that is n into n minus 1 into n minus 2 up to n minus r plus 1, or simply we say that NPR equal to P of n comma r equal to n factorial by n minus r factorial. That is, here n objects for r selection of objects is given by P of n comma r. We see one problem, one example in permutation. How many three-letter words with or without meaning can be formed out of the letters of the word swing when repetition of letters is not allowed? Here the given word is swing. We have to calculate how many three-letters words with or without meaning. Here the meaning is not important. We have to form three-letter words using the word swing. How many three letters word we have to formed when repetition of letters is not allowed? Here n equal to 5. Since in the word swing we have 5 letters, therefore we take n equal to 5. As the word swing has 5 letters, since we have to frame 3-letter words with or without meaning and without repetition, therefore total permutations possible are P of n comma r equal to P of 5 comma 3. That is NPR equal to 5P3. That is n factorial by n minus r factorial. That is 5 factorial by 5 minus 3 factorial. That is 5 factorial by 2 factorial. That is equal to 6. We have to form 60 words, 3-letter words with or without meaning from the word swing. Here the repetition of letters is not allowed. The next topic is combinations. Combination means selection of objects or any things. We know permutation means arrangement of objects. Combination means selection of objects. Here order is not important. We denote combinations by the letter. We represent combinations by NCR. NCR equal to NPR by R factorial. Already we know that NPR equal to n factorial by n minus R factorial. Therefore, NCR equal to n factorial by n minus R factorial into R factorial. Now we see one example. The number of combinations of 5 objects taken 2 at a time is 5C2. That is, here we have to select 2 objects from 5 objects. Therefore, we write 5C2. 5C2 equal to 5 factorial by 5 minus 2 factorial into 2 factorial. The answer is 10. Whenever in problem the selection is we have to use combination. The arrangement means we have to use permutation. The formulas for permutation and combinations are called counting formulas, since they can be used to count the number of possible permutations or combinations in a situation without having to list them all. Next one important topic is recurrence relations. Um, we see the definition of recurrence relation. The recurrence relation for the sequence AN is an equation that expresses AN in terms of one or more of the previous terms of the sequence, namely A0, A1 up to AN minus 1 for all integers n with n greater than or equal to n0, where n0 is a non-negative integer. That is, any equation that expresses in terms of an or the previous terms of an is called recurrence relation. A sequence is called a solution of the recurrence relation if its term satisfies the recurrence relation. The initial conditions for a sequence specify the terms that precede the first term where the recurrence relation takes effort. You see one example for recurrence relation. Let an be a sequence that satisfies recurrence relation an equal to an minus 1 plus 3 for n equal to 1, 2, 3, 4, etc. And suppose that a naught equal to 2. What are a1, a2 and a3? Okay, here given that the recurrence relation an equal to an minus 1 plus 3 and also given the initial condition is a naught equal to 2. We find the value of a1, a2 and a3. Okay, here substitute n equal to 1. Here given the values of n is varies from 1 to infinity. Here substitute n equal to 1, we have a1 equal to a naught plus 3. Already we know that a naught equal to 2. Therefore, a1 equal to 2 plus 3, that is a1 equal to 5. In the same way, we can calculate a2, a3 up to a2, a3, a4 up to etc. This is also the same problem, same type of problem. Here A and B is sequence that satisfies the recurrence relation an equal to an minus 1 minus an minus 2 for n varies from 2, 3, 4 up to infinity, and suppose that a naught equal to 3 and a1 equal to 5. What are a2 and a3? Now we see the difference between these two recurrence relation. Here an equal to an minus 1 plus 3. Here an equal to an minus 1 minus an minus 2. This recurrence relation consists of an and the previous terms of an, that is an minus 1. This is constant term. This is a recurrence relation, but non-homogeneous recurrence relation. Since this equation consists apart from the terms, previous terms of an. But this recurrence relation is called homogeneous recurrence relation. Here all the terms are an and the previous terms of an. Therefore, it is called homogeneous recurrence relation. It is non-homogeneous recurrence relation. For here for n equal to 2, 3, 4, and suppose that a naught equal to 3 and a1 equal to 5. Now we find what are the value of a2 and a3. Here substitute n equal to 2, a2 equal to a2 minus 1, that is a1 minus a naught, 5 minus 3, therefore a2 equal to 2. The same way we calculate a3. Fibonacci sequence is one best example for recurrence relation. That is, Fibonacci numbers are defined by f0, f1, f2, etc. Here the initial conditions is f0 equal to 0 and f1 equal to 1. Now we write the recurrence relation for this Fibonacci sequence, that is fn equal to fn minus 1 plus fn minus 2. Here n equal to 0 means we get, that is n varies from, here n varies from 2, 3, 4 up to infinity. Here we substitute n equal to 2, f2 equal to f2 minus 1, that is f1 plus f0. The first term in the Fibonacci sequence, the first term is 0, the second term is 1. Now we find the third term. For finding third term in this recurrence relation, we substitute n equal to 2. We get f2 equal to f2 minus 1 plus f2 minus 2. That is f2 equal to f1 plus f0. f2 equal to f1 plus f0. f2 equal to 1 plus 0, that is f2 equal to 1. The third term is 1. Now we find the fourth term. For finding fourth term, we substitute n equal to 3. f3 equal to 3 minus 1, 2. f2 plus f1. f2 plus f1. We know that f2 is 1, f1 is 1. Therefore, f3 equal to 1 plus 1, that is 2. f3 equal to 2. The same way we find f4, f5, f6, f7, etc. Okay. And the Fibonacci sequence is 0, 1, 1, 2, 3 comma 5 comma etc. The first term is 0, second term is 1, the third term is we add first and second, we get third, we add second and third, we get fourth term, third and we adding third and fourth, we get fifth term. That is Fn equal to Fn minus 1 plus Fn minus 2. This is the recurrence relation for Fibonacci sequence. This is best example for recurrence relation. Now we see linear homogeneous recurrence relation. There are two types of recurrence relation. One is linear homogeneous recurrence relation. Another one is linear non-homogeneous recurrence relation. First one is linear homogeneous recurrence relation. A linear homogeneous recurrence relation of degree k with constant coefficients is a recurrence relation of the form an equal to r1 an minus 1 plus r2 an minus 2 plus etc. plus rk an minus k. This is homogeneous recurrence relation. Since in this recurrence relation all the terms are an and the previous terms of an etc. Okay. Here R1, R2 up to Rk are real numbers and also Rk not equal to 0. Okay. Since it is linear because the right hand side is the sum of the previous terms of the sequence. Sum of the previous terms of the sequence each multiplied by a function of n. And the next one is it is homogeneous because no terms occur that are not multiples of the AJs. Okay, except an, there is no term occurs. Except an and the previous terms of an, no other terms are occurs. Therefore, it is homogeneous. Each coefficient is also a constant. The degree is k because an is expressed in terms of the previous k terms of the sequence. These are the linear homogeneous recurrence relations. This equation Pn equal to 1.11 of Pn minus 1. It is linear homogeneous recurrence relations of degree 1. This Fibonacci sequence is an example for linear homogeneous recurrence relation of degree 2. This recurrence relation is not linear. It is not linear since here an equal to an minus 1 plus an minus 2 square. Therefore, it is not linear. This recurrence relation, that is hn equal to 2hn minus 1 plus 1. It is not homogeneous since here the constant term occurs. This is the sequence, this term 1 is not a sequence of hn. Here the constant term occurs, therefore it is not homogeneous. This recurrence relation Bn equal to n into Bn minus 1. This is recurrence relation, but here coefficients are not constants. These are some examples for recurrence relations. Next we see how we solve non-homogeneous linear recurrence relation. The recurrence relation with the definition is linear because the right hand side is a sum of previous terms of the sequence, each multiplied by a function of n. Okay, these are we already see. Now we see how we find the solution of the recurrence relation. We see one example. Find the solution of the recurrence relation an equal to an minus 1 plus 6 an minus 2 given a not equal to 1 and a1 equal to 2. This is the homogeneous recurrence relation since all the terms are sequence of an. And also given initial condition is a not equal to 1 and a1 equal to 2. The first step of the solution is we write the characteristic equation of the given recurrence relation. We write the characteristic equation of the given recurrence relation. Now we write the given equation. We rewrite the given equation as in this form, that is an minus 1 minus 6 an minus 2 equal to 0. Okay, this last term is constant term or square term, or that is constant term x square term. Therefore, the characteristic equation of this recurrence relation is x square minus x minus 6 equal to 0. Now we factorize this equation. It is a quadratic equation in x. Therefore, this equation having two roots. Okay, that is x plus 2 into x minus 3 equal to 0. Therefore, x equal to minus 2 comma 3. X equal to minus 2 comma 3 are solutions of this recurrence relation. Here the roots are real root and also different root. Therefore, the solution equal to an equal to alpha 1 into this r1 power n, first root power n, plus alpha 2 into r2 power n. Here the roots are real but different roots. Therefore, here we write the solution as the general form of the solution is an equal to alpha 1 into r1 power n plus alpha 2 into r2 power n. Now, using this initial conditions a0 and a1, we find the constant value alpha 1 and alpha 2. That is, now substitute n equal to 0 for this equation. We get a0 equal to alpha 1 into minus 2 power 0 plus alpha 2 into 3 power 0. a0 equal to alpha 1 plus alpha 2. We know that a0 equal to 1. Therefore, 1 equal to alpha 1 plus alpha 2. In the same way, a1, given that a1 equal to 2. Therefore, we substitute here n equal to 1. a1 equal to alpha 1 into minus 2 power 1 plus alpha 2 into 3 power 1. That is minus 2 alpha 1 plus 3 alpha 2 equal to 2. Solving these two equations, we get alpha 1 equal to 2 by 3 and alpha 2 equal to 1 by 3. Now substitute alpha 1 and alpha 2 value in an, we get 2 by 3 into minus 2 power n plus 1 by 3 into 3 power n is the solution of the recurrence relation. Okay. Using the given initial conditions, we find the constant value in an. The next heading is linear non-homogeneous recurrence relation with constant coefficients. This non-homogeneous recurrence relation is in the form of an equal to c1 an minus 1 plus c2 an minus 2 plus etc. plus ck an minus k plus f of n. Here c1, c2 up to ck are real numbers and f of n is a function of n not identically 0 depending only on n. Okay, this is non-homogeneous since all the terms are not a sequence of an. Here f of n is independent of an. Therefore, it is non-homogeneous recurrence relation. Now we write the associated homogeneous recurrence relation. For this non-homogeneous recurrence relation, we omit f of n. We write the recurrence relation, that is an equal to c1 an minus 1 plus c2 an minus 2 plus etc. plus ck an minus k is called the associated homogeneous recurrence relation. Now we see how we find the solution of this non-homogeneous recurrence relation. Now consider non-homogeneous linear recurrence relation, that is an equal to an minus 1 plus an minus 2 plus 3 power n plus n 3 power n plus n square plus n plus 3. Here f of n is this whole term. This is f of n. These parts are independent of an. Now we write homogeneous part of this recurrence relation. This part 1 is homogeneous part. Now which we now call it as associated linear homogeneous recurrence relation. Okay. Now we find as usual the solution of this associated homogeneous recurrence relation, that is denoted by a n power h, a n power h. Then then we find the solution of this f of n, that is particular solution. Here part 2 is of our interest in this section. It is the non-homogeneous part. Solving this kind of questions are simple. You just need to solve the associated recurrence relation. Then solve the non-homogeneous part to find its particular solution. Okay, therefore the solution an equal to an power h plus an power p. That is the solution of a associated homogeneous recurrence relation and the solution of and we find particular solution. Here now we see non-homogeneous recurrence relation, that is fn equal to a into fn minus 1 plus b into fn minus 2 plus f of n. Okay. Here f of n is independent of this fn. Its associated homogeneous recurrence relation is fn equal to a into fn minus 1 plus b into fn minus 2. The solution an of non-homogeneous recurrence relation has two parts. First part is the solution of associated homogeneous recurrence relation. Second part is the particular solution. That is an equal to ah plus at. In non-homogeneous recurrence relation, the term f of n is of the form k power n. Then we see how we find the solution of this type. Given example is solve an equal to 3an minus 1 plus 2 power n. We first proceed to solve the associated linear recurrence relation, that is associated homogeneous recurrence relation for this equation is an equal to 3an minus 1, that is an minus 3an minus 1 equal to 0. Now we write characteristic equation for this equation, that is r minus 3 equal to 0, r equal to 3. Okay, there is only one root. Therefore, the solution is an equal to c1 into r1 power n. That is an equal to c1 into 3 power n. Next, we find the solution of this non-homogeneous part. Here here f of n equal to 2 power n. F of n equal to 2 power n. Therefore, we substitute in this non-homogeneous recurrence relation in place of an c2 into 2 power n, and in place of an minus 1 c2 into 2 power n minus 1. That is an equal to 3 an minus 1 plus 2 power n we have. In place of an c2 into 2 power n, in place of an minus 1 c2 into 2 power n minus 1 plus 2 power n. Here in both the terms 2 power n is common. Therefore C2 minus 1 into 2 power n equal to 3 C2 2 power n minus 1. 2 power n getting cancelled. We have only here 2. That is 3 C2 equal to 2 C2 minus 1. 2 C2 minus 1 equal to 3 C2. And so we have C2 equal to minus 2. C2 equal to minus 2. Which then gives us an equal to minus 2 into 2 power n, that is minus 2 power n plus 1. Already we know an equal to c2 into 2 power n. We assume that the solution of this non-homogeneous part is an equal to c2 into 2 power n. Now we find this constant value c2. This constant value is c2. For finding this constant value, we substitute in the given recurrence relation in place of an C2 into 2 power n, and in place of an minus 1, C2 into 2 power n minus 1. Then simplifying these equations, we get the value of C2. It is constant value. C2 equal to minus 2. Therefore, an equal to minus 2 into 2 power n, that is minus 2 power n plus 1. Now we get the general solution an equal to the solution of associated homogeneous recurrence relation plus particular solution. Here the solution of associated homogeneous recurrence relation is C1 into 3 power n. The solution of particular solution is minus 2 power n plus 1. Adding these two, we get the general solution. Here the initial condition is given a naught equal to 2. Using this a naught equal to 2, we find the constant value C1. Okay, we substitute n equal to 0, we get a naught equal to C1 into 3 power 0. Anything power 0 is 1. Therefore, here we get only C1 minus 2 power 1. A naught equal to C1 minus 2. So, simplifying this, we get C1 equal to 4. Therefore, an equal to 4 into 3 power n minus 2 power n plus 1. Okay, suppose in non-homogeneous recurrence relation, the term f of n contains k power n, that is k is any constant, the base k is any constant, that is 2, 3 or 4 etc. Any numerical number. Then we find the particular solution in this way. We assume the solution is the constant into the constant into 2 power n. Suppose here this base 2 is not the root. Here the root is 3. But here our base is 2. This 2 is not a root. Therefore, we take the solution is of the form an equal to one constant. That constant may be anything, C1, C2 up to Ck. Constant into 2 power n. Suppose this 2 is root of our problem, then we take the solution is of the form n into C2 into 2 power n. Okay, this 2 is double root of our problem, then we take n square into C2 into 2 power n. Here we see the type of problem, that is an equal to 2 an minus 1 plus 2 power n. In this recurrence relation, first we find a solution for associated homogeneous recurrence relation, that is an equal to 2 an minus 1. Then the characteristic equation is an. Then the recurrence relation, associated homogeneous recurrence relation is an minus 2 an minus 1 equal to 0. The characteristic equation for this recurrence relation is r minus 2 equal to 0. We get r equal to 2. Here, that is therefore the solution is an equal to C1 into 2 power n, which has the same form with the non-homogeneous part. In this case, we need to multiply our homogeneous part with n, which means we take an equal to n into C1 into 2 power n. Since here our base 2 is one root of our recurrence relation, associated homogeneous recurrence relation. Therefore, we take an equal to n into C1 into 2 power n. The same way, an minus 1 equal to n minus 1 into C1 into 2 power n minus 1. And using the same method, we find the solution is nc1 equal to 2 power n equal to 2 into n minus 1 into c1 into 2 power n minus 1 plus 2 power n. Now we substitute the value of an and an minus 1 in the given recurrence relation. When simplifying this, we get an equal to c1 into n into 2 power n plus c2 into n square into 2 power n. Now we see the next problem, that is an equal to 2 an minus 1 plus 3 2 power n plus 5n into 2 power n. Here this is this two terms are f of n. This is independent of the sequence of an, therefore this is f of n. And in this problem we write associated homogeneous recurrence relation is, that is an minus 2 an minus 1 equal to 0. An minus 2 an minus 1 equal to 0. That is, the characteristic equation is r minus 2 equal to 0, r equal to 2. R equal to 2. Therefore, we write that is an equal to c1 into n into 2 power n plus c2 into n square into 2 power n. In this problem, we have r equal to 2, which has a double root. Since here we have r square minus 4, r square plus 4. We write the associated homogeneous recurrence relation for this equation is an plus 4 an minus 2 plus 4 an minus 2 equal to 0. Therefore, we having r minus 2 into r minus 2 equal to 0, r equal to 2 comma 2. R is a double root. Therefore, then we have non-homogeneous part is an equal to c1 into n square into 2 power n plus c2 into n cube into 2 power n. In this way, we have to solve non-homogeneous recurrence relation. The next important topic is generating functions. Using this generating function, we have to solve a recurrence relation. We find the solution of the recurrence relation. This is the definition of generating function. The generating function for the sequence S with terms a0, a1 up to an of real numbers is the infinite sum. That is, we denote generating function by g of x, that is equal to g of s comma x equal to a0 plus a1x plus a2x square plus etc. plus an into x power n. Here in this term, all the terms are the sequence of an, that is a0, a1 up to an. We write this expansion in summation, that is summation n equal to 0 to infinity an into x power n. We write the generating function for this sequence 1 comma 1 comma 1 comma 1. We substitute in this term, in this equation, in place of a0, a1 up to an or 1, then that is 1 plus x square plus up to etc. x power n plus etc. This is a known formula. We know that that is 1 minus x whole power minus 1 is 1 plus x square plus etc. Therefore, 1 by 1 minus x, we write in terms of summation, that is summation n equal to 0 to infinity x power n. And we write the generating function for this sequences. The first sequence is 2 power 0, 2 power 1, 2 power 2, 2 power 3, etc. 2 power r. That is 2 power 0 means 1, 1, 2, 1, 2, 2 square, 2 cube, etc. Here we substitute, that is 1 plus 2x plus 2x the whole square plus etc. 2x whole power n. Therefore, summation n equal to 0 to infinity 2x power n. The same way we write the generating function for the sequences. Now we see how we solve a recurrence relation using this generating function. The first step is we rewrite the given recurrence relation as an equation with RHS equal to 0. Then the second step is multiply the equation by x power n and taking summation from 0 to infinity or 1 to infinity or 2 to infinity, depending upon the given initial conditions. Okay. Then the step 3 is we use the generating function in our equation. The generating function is summation n equal to 0 to infinity an into x power n equal to g of x. Then we decompose g of x into partial fraction. Okay, when we use partial fraction means in g of x, in the denominator is the multiplication of two terms or more than two terms. Using partial fraction, we separate the terms. We separate the single terms. Then express g of x as a sum of Fibonacci series. That is using binomial expansion, we express the given term g of x. Finally, we find the solution an equal to the coefficient of x power n in g of x. In this g of x, we see what is the coefficient of x power n. That is the solution of recurrence relation. That is an equal to the coefficient of x power n in g of x. This following table represents some sequences and their generating functions. The sequence is 1 means the generating function is 1 by 1 minus z. The same way, minus 1 whole power n means the generating function is 1 by 1 plus z. Okay, these are the generating function for the sequences. Now we see one problem using generating function. How we solve recurrence relation using generating function. Problem is using generating functions, solve the recurrence relation an equal to 3an minus 1 for n greater than or equal to 1 with a not equal to 2. Here we introduce the generating function g of x. G of x equal to summation n equal to 0 to infinity an into x power n. Okay. We rewrite the given recurrence relation with RHS equal to 0, that is an minus 3an minus 1 equal to 0. Then the second step is multiply each and every term by x power n and taking summation from 1 to infinity. Since in the problem itself here given that n greater than or equal to 1, n varies from 1 to infinity, therefore taking summation from n equal to 1 to infinity. It is summation n equal to 1 to infinity an x power n minus summation n equal to 1 to infinity 3an minus 1 x power n equal to 0. Now using generating function, we solve this equation. That is now expand this summation we get, that is a1 x plus a2 x square plus a3 x cube. But our g of x is a naught plus a1x plus a2x square plus a3x cube. Therefore, we write instead of this g of x minus a naught, and also here minus 3x into g of x. Now here we multiply. Here we have 3an minus 1, but here x power n. We need the same terms an minus 1, and also here also we want 3 x power n minus 1. Therefore, we multiply x power minus 1 into x. Therefore, minus 3x into, we expand this, we get the same g of x. Therefore, here we substitute g of x. G of x minus, given that a naught equal to 2, therefore g of x minus 2 minus 3x into g of x equal to 0. We simplify this, we get g of x equal to 2 by 1 minus 3x. Here, the denominator is only one term, that is only one expansion, 1 minus 3x. Here that is 2 into 1 minus 3x whole power minus 1. We expand this 1 plus 3x the whole square plus etc. We know that an equal to coefficient of x power n in g of x. That is 2 into coefficient of x power n in g of x, an equal to 2 into 3 power n. This is the solution of the given recurrence relation, an equal to 2 into 3 power n. Now we see GATE questions asked in previous years. The first question is, in a group of 6 boys and 4 girls, 4 children are to be selected. In how many different ways can they be selected such that at least one boy should be there? Okay, this is a selection process. Therefore, we have to apply combination. Okay, whenever in problems the selection is comes, we have to apply combination. In a group, we have 6 boys and 4 girls. That is totally 10 students. We have to select only 4 students, 4 children. In how many different ways can they be selected such that at least one boy should be there? In a group, already one boy, at least one boy should be there. We see the solution. In a group of 6 boys and 4 girls, 4 children are to be selected such that at least one boy should be there. Hence, we have 4 options as given below. We can select 4 boys from 6 boys. Number of ways to this 6C4. The second option is we can select 3 boys and 1 girl. Is 6 boys and 1 girl means 3 boys and 1 girl means we can select 3 boys from 6 boys. Therefore, 6C3 into and select 1 girl from 4 girls. Therefore, 4C1. 6C3 into 4C1. The same way, option 3, 2 boys and 2 girls, and 1 boy and 3 girls. Okay, we have to select 4 children from 6 boys and 4 girls. 4 children may be first option. Uh, there is no girl. All 4 are boys. The second option is 3 boys and 1 girl. Third option is 2 boys and 2 girls. Fourth option is 1 boy and 3 girls. The fifth option is not come. All are 4 girls or not come, since here the condition is at least one boy should be there. At least one boy should be there. Therefore, the total number of ways is we have to add these 4. We get the answer is 209. Okay, understand? Here we have to select 4 children. The given condition is in that group, at least one boy is already there. At least one boy means minimum one boy is there, maximum 4 boy are there. Therefore, the first option is we can select 4 boys from 6 boys, that is 6C4. Second option is 3 boys and 1 girl. Third one is 2 boys and 2 girls. Fourth one is 1 boy and 3 girls. Therefore, we add all these 4, we get the answer is 209. The second problem is how many ways are there to arrange 7 chocolate biscuits and 12 cheesecake biscuits into a row of 19 biscuits. Okay. Here we have totally 19 spots and filling them with 7 chocolate biscuits and 12 cheesecake biscuits. Okay. Then we just choose 7 pots for the chocolate biscuits and let the other 12 spots have cheesecake biscuits. Therefore, the answer is 19C7. The total spot is 19. We have to arrange 7 chocolate biscuits and 12 cheesecake biscuits. Therefore, we take the answer is 19C7. The same way, the next question is Amit must choose a 7-digit PIN number and each digit can be chosen from 0 to 9. How many different possible PIN numbers can Amit choose? This problem comes under the counting principle, basic counting principle. We have 10 chances for each position, each digit. First digit we have the chances from 0 to 9. Therefore, 10 choices. The same way, 7 places we have 10 choices. Therefore, the answer is 10 into 10 into 10 into 10 into 10 into 10 into 10. Okay. The next problem comes under recurrence relation. Here consider given recurrence relation is an equal to 5n plus an minus 1. The initial condition is a1 equal to 4. We find the value of a64. This is non-homogeneous recurrence relation since this term 5n is not a sequence of an. Okay. Okay, that is an equal to 5n plus an minus 1. We rewrite this equation as 5n. The next term is 5 into n minus 1 plus 5 into n minus 2 plus etc. plus an minus 2 plus an minus 1 plus etc. Last term is a1. Since we are given that a1 equal to 4, a1 equal to 4, we substitute a1 equal to 4. We simplify this, we have this equation. It is 5 into the previous term is here 5 into n minus 2, then 5 into n minus 3, etc. Here 5 into 1 minus 4. The last term is 4. Here given that this term is 4. Therefore, 5 into we write this 4 as 5 into 1 minus 1. In all the terms, 5 is common, taking outside. 5 into n plus n minus 1 plus n minus 2 plus etc. plus 2 plus 1 minus 1. This is sum of n natural numbers, that is n into n plus 1 by 2, 5 into n into n plus 1 by 2 minus 1. Okay. We simplify this, we get an equal to 5 into n plus 1 by 2 minus 1. Yes, substitute n equal to 64, we get this answer, that is 10,399. Therefore, the answer is A, first one. Next, we see the solution of this recurrence relation. The given recurrence relation is an equal to 6 an minus 1 minus 8 an minus 2. The initial conditions are a not equal to 3 and a1 equal to 5. This is a homogeneous recurrence relation. Therefore, as usual, we first write the characteristic equation of this recurrence relation, that is x square minus 6 plus 8 equal to 0. By solving this characteristic equation, we get two roots, x equal to 2 and x equal to 4. Okay, these two roots are real and also different. Therefore, the solution is an equal to a into 2 power n plus b into 4 power n. Now, using this initial conditions a not equal to 3 and a1 equal to 5, we find the value of a and b. Okay. A and b value is a equal to 7 by 2 and b equal to minus 1 by 2. Therefore, the solution an equal to 4 into 2 power n minus 1 into minus 1 by 2 into 3 power n. 4 into 2. It is, the solution is a is 7 by 2. 7 by 2 into 2 power n minus 1 by 2 into 3 power n. Thank you. Thank you very much for giving me an opportunity.